Here I am Vadel Sagar. Welcome back in the part number 16 of our present discussion of the chapter number 1. So without wasting time, we are in the part number of 15th part, the applications of Gauss law. That you may found out in the 15th number part, that first slide which I kept it again here. Why we are reducing the electric field formula for the particular shape of modules. For this, last time we seen that reduce our formula to the our thin wire. We derive the electric field formula for the thin wire, infinitesimal thin wire. Today we go for the thin sheet and one thin spherical surface. So why we are okay, so whenever we got some such type of objects, so you can directly use the formula easy way using Gauss law. Electric field you can able to derive instead of one more other way. It is you have to do this is summations and all the volume elements or the surface element you have to take and integrate over there. So in all cases you can't do these things. You can use the Gauss law and you can generate. Okay, now the 1.15.2, filled due to infinitesimal charge infinite plane sheet. So this is your plane sheet. This is a blue shadowed part. This is not a hollow. This is a infinitesimal plate sheet. It means I can say your notebook one page is your infinitesimal thin plane sheet. On this one notebook paper, it is a one plane, it's containing a charge. Now what is electric field? It depends on the how what charge it can contain, positive charge or negative charge. So suppose it is a positively charged whole page, then it is a generating electric field. Now you have to take any reference points outside to the space, and according that you can judge your Gaussian surface, and you can able to judge how much electric field passes through the Gaussian surface. It is your flux, and throughout this we can do the calculation using the flux scenario. Why comes into picture? Because the using Gauss law we are trying to derive the electric field. So using the flux through, we will end up with the theory as we seen in this infinitesimal long wires. Here also same task, we go for the first deriving the flux according to the our basic knowledge about the electric flux, and then we use a Gauss law, and at the end we derive the electric field of the infinitesimal plane sheet. So here the sigma is the uniform surface charge density, because the paper is a one surface, and whatever the charge it contain, it is on the small part we are integrating all over this, so that it has a surface charge density which is symbolized as a sigma. This is sigma. Okay, we take the x as a normal axis from the plane sheet. So here the plane sheet is the in this standing like, so this x axis is the likewise. So this whatever the coordinate or calculation comes into picture, which is a normal to the x axis, it means our plane of sheet which is perpendicular to the x axis, and then y and z are the parallel to the our plane sheet. So this will be now electric field which is present in this x axis, because the charge are present here. So either it can be this side, either it can be this side. So charge electric field is not present in this side. If I am as you know, the surface element delta s vector, if you want to draw, which is always normal to the surface, then it will be this side or it can be this side. So it is parallel to the E. So only the x directional calculations only can survive, because the y and z coordinates are not making angle 0. They makes an angle with the electric field, because electric field is present here and they are the in a respective axis. So they makes an 90 angle. So this will be not survive, cos will not survive. That you already know this. The electric field will not depends on the y and z coordinate, because they're 90 angle at the only the x is the parallel to the directions. We can take the Gaussian surface, the rectangular parallelogram, that is instead of this blue sheet, you whatever you are seeing, which is your Gaussian surface, through which how much electric field which pass and how much flux will pass, that you have to calculate. Now as you know also, this 1 and 2 sheet, this parallel sheets are to the parallel to the your infinitesimal plane sheet original one, only having the flux ratio. This whatever the side, upside downside, or this is the, it means you have one box, so only the two side of this box only containing the electric field of the present sheet. The above and down or the front or back of this box will be not having any electrical flux, because the the flow of electric field is this only. Okay, so this is a parallelogram we are taking as a Gaussian surface, and whose area of this whole system will be the A. Now then the so here some mismatching are there due to this delta is not coming in the mobile version, so that's why I'm using the pictorial form of it. But delta S is shift to the is this side, so see, therefore the flux E dot delta S, we know the flux is always defined as a E. It means electric field multiplied by the surface element through the both the surfaces are equal and add up through the both the surfaces, and equal and add up. So therefore the net flux through the Gaussian surface is 2E. So net flux. Okay, now what is the flux through this? Now we cannot do the all time the mathematics here. See, the flux through pass through this first element or the first surface part, okay, which is the phi 1. You can able likewise phi 1 E time delta S, where delta S is the area of this surface, which is A for you. Okay, so this is the flux through this E time A. Now flux through this also, because the direction is of E is independent both each other, so it is not negative sign will contributing, both are the having independent flux of it, both directions E it has. Okay, so now in the second way, E dot delta S also surviving E time of A. Delta S is going to be A, is the area. So sheet A is also having flux E time A. Sheet 2 is also having flux E time A. So the total flux of the system due to this present sheet, it will be 2 time of EA. The charge enclosed by the surface is delta S. Delta S is here. Therefore, the Gaussian's law is, now what I am just said, that phi is equal to E time delta S, which is delta S is nothing but the area element. Actually not area element, and but if the area element is integrating over the all deltas, then it will be reduces to the total A. The two side faces are that total phi is equal to 2 time of E. Then this our phi, it means the flux passed through the Gaussian surface 2 time of EA. So whatever this A, it is the area of Gaussian surface, not the area of the sheet which you are taken. And as per our knowledge of the Gauss law, the phi is equal to reduces by Q upon epsilon 0. And our the continuity charge distributions point of view, this is I am doing this some extra term for you. Sigma is the surface charge density is equal to Q by A. A is multiplied to the sigma, then sigma time A is equal to Q. So the Q, it is replaced by the sigma time A upon epsilon 0 is equal to 2EA, where AA is cancelled out from the both sides, then E is equal to sigma time 2 epsilon 0. This is the electric field can generate by the plane sheet who's having particular charge sigma charge density. And if this electric field is, if you want to write in the vectorial form, E vector is equal to sigma upon 2 epsilon 0 into the n cap. N cap is the particular the normal directions it is showing to the plane sheet. This is a plane sheet and this is the normal directions, towards that directions only electric field can be. Okay, now we go for the some new applications, and this we can end up with the here also the E can be positive when it is a the charge is going to be outward, and E can be negative, charge is going to be inward. That the some conclusive line it is given in the textbook also. Okay, now 15 for topic and the third subtopic of its. Now we are go for the deriving the electric field for the infinitesimal spherical shell. Now this is a blue part, this is our task, this is our object, original object, that you can able to see the surface charge density which lies on this spherical surface is sigma. This is one ring, like it means your તમે જે VT પહેરો છો ને like that, it is a exactly spherical. No, not that VT one. Marble, if you have one marble and you are just cave out all the elements which are present inside, and that thin surface you have. That exact example if I want to give you, that is your soap bubble. Soap bubble is only spherical thin sheet. Okay, so forget it about that ring, forget about the uh, marble. Exact examples of this thin spherical shell is the soap bubble. That is here the let sigma is the uniform charge density which are present in the, it is a one surface, there is no volume inside, so it is a surface which is spherical surface, and the charge which are present, it is a sigma. The field at the point anywhere, if the charge which are present on the spherical surface, if you have a soap bubble and on it you are generating a charge, then due to this presence of charge, the electric field is generated around the soap bubble. At somewhere you are choose your points, anywhere outside to the your soap bubble, anywhere you are choosing the P point. Through the P point whose particular radius from the center, the P point, you have a one sphere also, imaginary sphere, and that is imaginary one shape, which is nothing but the Gaussian surface. So all over the all the P point, all P point, it means anywhere, not only circle on the whole sphere, anywhere the electric field will be the same, because the electric field not depends on the yes, electric field is depends on the radial distance, and radial distance of the all the P's whatever are present on the sphere, which is same, r, small r1. And the soap bubble or the our thin spherical shell, whatever you are taking, whose radius is capital R, the field, now you have two more options inside subtopics. The field outside to the cell, now our P point which you are, the presence of electric field which you are testing outside to the your bubble, and you have may also electric field can be possible inside the bubble also, there we will see in the later section. But now for our P point, the observational point which is lies outside to the bubble or the cell, the field outside to the cell, the Gaussian surface whose radius is r, that you can able to see from the observations point, or you can able to see the center of the sphere. The each point on the Gaussian surface has the same magnitude of E. Anywhere on the Gaussian surface point will be the same magnitude of E, as I explained you, because the r is same for the all the vectors of the each radial vectors. Okay, and this is what we have now. This is our sort of calculations. The radius of the Gaussian surface is r, as you can able to see. The radius of the your spherical shell, which is capital R. Then the flux which is passed through the Gaussian surface, flux passes through the Gaussian surface due to presence of this ring or the spherical shell who's containing a charge. Then the flux is E times delta S, where your delta S is the area of the spherical Gaussian surface, not the spherical area of shell. Why? Because flux which is passed through the Gaussian surface, not passed through the, because the spherical shell is the generating this electric field, and electric field will pass through the Gaussian surface, and it is a, there you are finding the flux. So there this delta S is the area element of the Gaussian surface, and Gaussian surface is radius is small r. So this area is integrating over all, so the all area of this Gaussian surface is 4 pi r square. Is it okay? Okay. Phi is equal to E times 4 pi r square, and this phi now it reduces using the Gauss law, q upon epsilon 0 is equal to E 4 pi r square, and this again it will be sigma, or the sorry, q is reduces to the, using the continuity charge distributions, the sigma time a. That sort of where a, now this a is not a area of the Gaussian surface, because the charge were present, the charge is present on the spherical shell, and then spherical shell area is the 4 pi r square, capital R square, because the whose radius is capital R square. So now this a is reduces to sigma times 4 pi epsilon, sorry, 4 pi r square, capital R square upon epsilon 0 is equal to E times 4 pi r square, where 4 pi is cancel out from the each other, so the E is defined as a sigma time r square upon epsilon 0 r square. Now where the sigma is reduces to, because the 2r cannot present inside the same electric field formula, otherwise it makes confusion. You can also calculate but we can reduce sigma is equal to q upon 4 pi r square, and r square cancel, so it is reduces to the q upon 4 pi epsilon 0 r square. This formula you can directly write from this. You can see this is e here, 4 pi r square you can take downside, this will be the here, so though no need to introduce these things also. But yes, for why I am putting or why book or why they are explaining to you, because their presence of capital R is also affecting on the equations, that you may also get an idea. But at the end, electric field which is not depends on whatever the electric field which is passed through the your Gaussian surface is not depends on what R you have, what spherical shell, how much bigger you have, that will not depends. Where you are Gaussian surface taken, it means what R you are taken, small r of the Gaussian surface, that is important at the end of the equations of the electric field. E is equal to q upon 4 pi epsilon 0 r square, where the vectorial form of it is looks like a q upon 4 pi epsilon 0 r square into the r cap in the particular direction, this one, where your p observation point you are taken, through which it is the electric field, it can be r vector. And this is what E is exactly the field produced by the charge q, which is present at the center of O. This is exactly the same as what we have in the center. Now the field is inside the cell. Actually the charge is not present at the center, charge is present at the surface. But somewhere in 11th class we discussed any charge which are present on the yes, in this 8th chapter of the earth, the mass of the earth is a whole system, earth has whole mass, but the mass is concentrated at the center of the earth. So like that, the charge is on the surface, but it behaves like at the center, but actually it is not at the center. Now what happened in this, what when we are taking the point of observations at the p point of observation point, which is inside the cell. Okay, the point is inside the cell, the Gaussian surface is again this through the center, is the center of O. The flux through the Gaussian surface calculated as before what we are did, E is equal to 4 pi r square, where your r square, this is easy na, the same task you have to do. Then phi is equal to E time 4 pi r square, where your r is the radius of your Gaussian surface which is inside the surface, so the 4 pi r square. However, this is the Gaussian surface is enclosing no charge. What Gaussian surface you are taken, but there is no charge is enclosed inside the surface. So as we are learn in the significance of the Gauss law in the part number 13 or 12, which is very important, if any Gaussian surface is not enclosing, any अंदर जो कोई charge ना होए, enclosing, there is no charge, then it can have no flux. Then the flux is equal to 0. E is equal to 4 pi epsilon r square is phi, and phi is 0, then the E is 0. The E cannot be there. Electric flux is also cannot be there. If your R, it means small r of your Gaussian surface is less than your capital R, it means what the system you have. Thank you very much.